Hi, the lecture today is about definite integral. Okay, in the last lecture we learned about calculating the area under a reasonable looking function. So I could have y is equal to f of x. It's a positive continuous function, and I might be limiting myself to the lines A and B, and on the bottom with the x-axis itself. We learned how to calculate the area that is limited by these lines. You remember the process started by subdividing the interval from A to B to several intervals. We labeled the very first point as x0, next point as x1, next point as x2, and so on all the way to xn for the last point. We defined these regions, the panels, and calculated the area of each of them in some manner and then added them up. Okay, let's adopt a general notation that will work for all the cases we have looked at. General notation will be to go ahead and pick some arbitrary point in the very first interval and call it perhaps x1 star, and pick another point in the second interval, call it say x2 star, and so on all the way to the very last interval and call that xn star. What are the uses of these star x's? Well, they are going to play whatever role we want them to play. We could adopt them as the left point of the interval and come up with the left point rule. We could adopt them as the right point and come up with the right point rule. We could adopt them as a midpoint rule, or we could just adopt them as some arbitrary point in that interval. So any of these points are sitting exactly in that specified interval. How do we calculate the area? You say the area, approximate area, is equal to the base of each of these rectangles, which is going to be delta x, and then times the height of the rectangle at the chosen point. So if the point was on the left or on the right or in the middle or wherever else it was, we just choose the height at that point. So f is going to be calculated at that point. So that's going to be point x1 star. And then we go to the next interval and choose some arbitrary point there, find the height there, and build a rectangle at that location, whatever it is. That's going to give us the next height, f of x2 and x2 star, excuse me, and so on we go until the very last interval, the nth interval, has the point x star n in it. We calculate the height there, and if you multiply it by the base, you get the area. Then we get ahead and had a notation, a shorthand notation for this kind of a summation. We write it as sum of f of x I star, I ranging from 1 to n. So this summation indicates we are performing what we see in this parentheses. And then I have to multiply with my delta x. From now on, we gradually move the delta x on the right hand side to make it look more like a traditional notation. Either left or right would be fine. So this is the area of the rectangles. So area of rectangles is equal to that. Now, in many applications that we have in mind, we want to do something like this. but we really don't care about the area of anything. That the problem doesn't have anything to do with calculating area of any geometrical object or anything like that. So for that reason, and also for having a notation that is a bit cleaner than what we see here, we go to some other notation. First of all, the quantity we are calculating, as a limit of this, we are going to call it the definite integral. Kind of a generic name, so that there is no implication that we are talking about area or anything, any specific thing, so that nobody else will claim discrimination or whatever. Just choose a name that is neutral. Call it definite integral. And then we adopt a notation for it. The notation for it is something new that you need to learn. So here's a notation. We draw an elongated S. This is presumably an S, supposed to be kind of like this sigma stretched out. On that sign, we are going to put the starting point of our area A, ending point of our area B, the name of the function, here's f, followed by some variable name that is not used elsewhere, typically it's just an x, followed by differential of that variable, here is just going to be dx. That which is read the integral of f of x from a to b is exactly what we have been calculating as a limit of this expression. That is, this is the limit of sigma of f of x I star delta x. Now you can take this limit under a variety of conditions. The simplest condition to use for us is to say that the number of partitions go to infinity. You have many subintervals here. More advanced text, they are going to insist it to say that delta x goes to 0. Here, instead of saying n going to infinity, we might as well insist that the size of each panel goes to 0. For us, both of them refer to the same thing, and perhaps it's easier for you to learn about it in this way with n. Okay, let's go ahead and learn a few more things about this notation before we go on and talk about the properties of this. Okay, what are each of these pieces called? This funny symbol here, this elongated s, is called the integral sign. It's called integral sign, and this process itself is called integration. Okay, we see two numbers, one corresponding to the first wall and the other corresponding to the second wall. This is referred to as the lower limit. That's called the lower limit of our integration. This one then, of course, is going to be called the upper limit. Do not get confused by this word limit. We are not taking limit of anything. Limit here simply has the connotation of what you use it for in ordinary everyday usage. It's just the end of your region. Whatever you have inside the integral sign, this function, this is called the integrand. Dx, well, that's just a differential that you are familiar with. The letter that is used for differential has to match the letter that you have used for the function itself. Notice that we are calculating some number at the end. For example, when you are calculating area there, you come up with a number. So this whole integral, this definite integral, doesn't really have any variables in it. So for that reason, sometimes this variable x is referred to as the dummy variable of integration. So it is possible that somebody might call this x as a dummy variable. We saw that funny terminology once before. When a variable name is used without it ever showing up in the final calculation, it's referred to as a dummy variable. Another item that we have here and needs a name by itself is this portion. This portion is referred to as Riemann sum. Riemann was a famous German mathematician who worked on this topic and lots of other topics, and in his honor, this portion is referred to as a Riemann sum. So we are calculating a definite integral as a limit of a Riemann sum. Okay, we learned quite a few words. You are encouraged to use these words in your problems so that you become comfortable when they show up in the assigned homework elsewhere. Okay, we just mentioned that we are generalizing our notation and definition so that we get away from the concept of area. Let me go ahead and point an issue that might come up. Suppose we are looking at the issue of the definite integral or the issue of calculating area for a function that behaves like this. Meaning, sometimes it is above the x-axis, sometimes it is below the x-axis. So here is, say, my A, here's my B, and okay, what is the issue? The issue is that in this definition, as you see, for each panel, you're supposed to calculate your F. Suppose you have a panel here. You want to calculate that area. So what is so big deal about that? You're supposed to take an F here and multiply it with your delta x. Now the thing is that F here is negative. F here is negative. When you multiply by delta x, you are getting negative. That means for any of the area that is under the x-axis, you are making a negative contribution to your sum. All of these areas are going to be recorded as negative, and they are going to be taken off from these positive areas. Here you get a positive contribution, here you get a positive contribution, here you get a negative contribution, if you go by that formulation. Well, it all depends. Is that what you really want, or perhaps you want something else? If you actually own a patch of land and some road goes through it, and you want to measure to see how much land you have, of course it doesn't make sense to say the area below the highway is going to be considered negative, in the area above highway is considered positive. After all, when you want to sell it, you want to collect money for both of these things. You don't want to give this thing away or pay somebody else some money just to take it off of your hand. So that doesn't make sense. So in many problems, negative area does not have any good meaning attached to it. On the other hand, the problem originally might have meant something else. Like this could be a profit curve for some company. Perhaps here they're doing well, here they're losing money, and of course when you want to do net calculation, this is supposed to be taken off of those. So depending on what F really connotates, you have to be careful about the way you are going to go and handle the issue here. If you really want them to cancel each other out, you go ahead and perform this thing just the way it is written, and you don't mind that some portions are negative. If you really want the actual geometrical area, you have to calculate this portion separately, force it to become positive, and calculate those portions separately also, and add them to each other. Make sure that there is no subtraction being performed. So you have to be careful about the issue of signed area and the net area, and just read the problems carefully and make sure you know which one of them is meant in any given problem. Okay, in the previous lecture we had an example of how to go ahead and calculate an area from scratch. I hope you do several examples similar to that. Those kind of problems typically they go on for a good length of time, and they involve quite a bit of algebra, but they are all good exercises, and you want to make sure that you do at least 2 or 3 of them. So for next item, we are going to go ahead and talk about some rather trivial properties of the definite integral. Property number 1. Suppose somebody writes an integral sign. You're supposed to start at some place A and end at some other place B, and apply it to a function f of x dx. Now suppose our starting place and ending place is the same place, that is B is same as A. What's going to happen to this integral? Well, pause for a moment, think for yourself what it's supposed to be. Maybe go back to some of the previous pictures and judge from that one what the answer is supposed to be. There is a simple answer to this question. So pause for a moment and then come back. Okay, now suppose we go to the very beginning picture. This whole notation was designed to have a way of showing us this area. Now if the starting and ending place are the same, means this second red wall is right on top of the first one. They have been squeezed close to each other. So if that is the case, how much area will be left between the two of them? Well, of course nothing is left. If it is starting from A, if you have a picture looking like this, if this is your function, suppose here you have a function and you're supposed to have second wall somewhere, but you're pushing that wall to come in closer and closer to A until finally the second wall is just here. The first and second walls are on top of each other. So what would be the area that is limited by these two walls? Well, obviously the answer is just 0. So that's the first property. Integral from a point to itself is 0. Property number 2 is the following. In most of our pictures, we have assumed that A is on the left and B is on the right, and we went about our business assuming that's always the case. But suppose for some reason somebody writes B to A of same f of x dx. That is, now this is a bit more tricky. We have same A to B as before. It's just that somebody has announced this one as the first wall and this one as the second wall. What will happen to the whole thing? Well, you remember our delta x was the second point minus the first point. So our delta x in this case is going to be a minus b over how many subdivisions you have. So in delta x, always a is the second point excuse me, definition of delta x, whatever is written as the upper limit of the integral is going to be written first. Whatever is written as the lower limit of integral is going to be subtracted from that one. Of course, that's going to be just the opposite of what we have been using in this case. In that case, delta x would have been b minus a over n. So the sign of delta x in the two cases will be different. If you exchange a and b, delta x is going to flip its sign. So the net result of this whole thing is that the relationship between this definite integral and the one where a and b are in their usual places is that one integral is just a negative of the other one. So swapping the limits of integral, the lower and upper limit, if you swap them, the effect is that definite integral is going to be multiplied by a minus sign. Next property of definite integral is essentially calculating it for a simple case. Suppose I have a function that is a constant. Suppose I have a function that is a constant k, and I integrate it from a to b dx. What is that? Well, let's go ahead and do a quick picture. The function that we have is a function that is sitting at a fixed place y, and we are going from a to b. Well, let's go back to our very original definition. We were attempting to calculate the area limited by these entities, the two walls and the function. That area is easy to calculate. Can you quickly tell me what is the area? Well, you calculate the base, which is b minus a, times the height, which is k. That is exactly what you expect to get here. Height times the width of the interval from b to a. So if k is a constant, then the definite integral of it is simply that constant times the length of the interval on which we are integrating. Now we have some so-called linearity properties. We have noticed that calculating definite integrals kind of a lengthy process, at least the way we are doing it for the time being. And if we can simplify our task, it's going to help us plenty. Now, suppose we want to find a definite integral. Suppose I want to calculate definite integral of, say, x squared plus x dx from, say, from 0 to 1. Well, if I already know how to calculate the definite integral from 0 to 1 of the individual functions x2 and x, if I know the definite integral of the individual pieces, I'll start to wonder if there is a relationship between this one and those two? And the answer is a resounding yes. There is something that's going to save us a lot of time, which is so yes, you can integrate piece by piece so long as those pieces are either adding to each other or subtracting from each other or just multiplying by a constant. Exactly same kind of a rule that you had for differentiation. Let's go ahead and understand what this thing really means. Here, what you have in mind is to calculate the area under a function which is a sum of two functions. So some of these two functions might look something like this. So this could be the graph of y is equal to x squared plus x. And you're trying to find out the area between the left side at 0 and the right side, say, at 1. Now, the height of this function itself is a sum of two heights. That is, the function is a sum of two functions. One is the function x squared, and the other one is the function x. Any rectangle that you like to look at on the on any of those subintervals that you want to look at here is really made out of sum of two rectangles at exactly the same spot for these two curves. That is, if I add these two heights, I'll get the height here. That's what it means to add the two functions. So if you're trying to calculate the area of this interval, of this panel, that would be same as calculating the area of this panel and then that one separately and add them to each other. All that happens in this style of calculation on the right hand side, that you come here and calculate all of the areas under x squared separately and all the areas under x separately and add them to each other. Over here, what you're doing is that you're adding the individual components first. That is, you're adding these heights first, and then you're adding all the areas for all these subintervals. So linearity property simply refers to the fact that if you have several pieces that are added or subtracted, you can do the integration piece by piece. Let's go ahead and write the example for subtraction as well. If I have x squared minus x and I am integrating from any location to any other location, I can do the same thing by calculating the areas separately if I want for each function and subtracting later on. So in a sense, we are exchanging the order of operation. What are we talking about? Order of operation. Here you're adding first and integrating later. On this side, you're integrating first and then adding later. We have exchanged two operations of addition and integration. Similarly, subtraction and integration, the two operations, can be exchanged. You could do them in any order. Finally, if I had a function like 3x squared dx and I wanted to integrate it, well, this is a function whose height is exactly 3 times the height of x squared. So what I could do is to go ahead and integrate x squared dx, find the area under that, and then triple it later on. It's very important for you to understand the reasoning behind these properties. Draw a picture for the left hand side, draw a picture for the right hand side, and convince yourself that this is correct. The general statement of linearity is like this. If you are integrating from a to b and you have two functions, say f of x and another one, say g of x, and you want to multiply this one by a and multiply that one by b and add or subtract, then integrate, you are free to perform it in this way if you wish. First of all, pull the constants outside. Second, perform individual integrations separately. So this is called the general linearity rule. And I hope that you understood what is involved. Now we are going to go ahead and talk about some other properties of integration. Okay, the next property of integrals we are going to make plenty of use of is the combination property. The property doesn't really have a name. Calling it a combination property, it refers to the following simple idea. If you have a function and then you're considering it at 3 points, let's call them, say, A, B, and C. If you go ahead, integrate your function from A to B, and then go ahead, integrate it from B to C, what do you think you're going to get? I'll make a guess. A to B is just this area. B to C is this area. So obviously you are getting area from A to C of f of x dx. Nice thing about this combination property is that A, B, C don't have to be in this order. They could have any arbitrary order, and this is still true. If you go ahead and look at it in some peculiar order like this. Suppose you have a function and here are your 3 points, A, B, C. Now, from A to B is this area which is considered positive. If you go from B to C is this area. But since you are going from B to C, the effect is going to be negative. What is left? Integral from A to C, or area from A to C, which is this one, which is the result of subtraction of red and green. Red was this whole area, green was on the right hand side. If you subtract the green off of the red, you are going to be left with this purple area on the side. So for A, B, C, any set of arbitrary numbers, for arbitrary A, B, C, this property holds. Next set of properties that we have for definite integral is so-called comparison properties. These properties refer to the situation where you are comparing one function versus another, and then you want to compare the integrals of the same two functions. For example, if you have a positive function, so if f of x does not become negative, and then b is larger than a, then you can conclude that the integral from a to b of f of x dx is not negative either. What are we saying? We're saying if your function is sitting above the x-axis and you just go ahead and calculate that area under that function, you're going to get a positive number. Well, that was the interpretation from point of view of areas, but it is true whatever your interpretation of this integral happens to be. Another property is that if a function is larger than or equal to another function and you are integrating it over interval from a to b, then you can conclude that the integral from a to b of f is also going to be the integral from a to b of g. What is the meaning of this? The meaning is if you have one function, let's consider this g, and you have another function, consider it f. If f is above g, then the area that you calculate under f, this area, is going to be more than the area you calculate under g. So that is not all that complicated or hard to believe. Property number 3 is if a function is between two numbers. If the function f is at least some number m, at most some big number m, and you're integrating your function over ordinary interval from a to b, then you can conclude that integral of f of x dx is going to be at least equal to the integral you get by just using m. Let me go draw a picture for you. It will be very trivial on a picture. Suppose you have a function. Suppose you know it is larger than this little m. Suppose you know it is smaller or below this m. So if you are going to integrate it from a to b, then the area under the blue is going to be less than area under the actual curve, which in its own turn is less than the area under that top function, the black function, all the way up there. So what do we get? What is the area under this blue curve here? That's going to be base, which is b minus a, times the height, that is m times b minus a. That area is less than the area under the function f itself. If f is limited from its above by this ceiling, by this capital M, then the area under f is also less than the area under that, which is m times b minus a. So these are rather trivial properties of definite integrals. When you're comparing two functions, the integral is going to reflect the inequality that you had. So long as you're integrating in the positive direction, b is larger than a, whatever inequality you have for the function translates to an inequality for its definite integral. Now, I guess I'll stop this lecture here. I hope that you read through the text and do several problems from this section. Good luck and God bless.